All right, I do want to address something that I stumbled over before. We're talking about transformers before we do anything on quantum. I call this the primary, and secondary over here.
Is it a mousetrap?
Sure. Mousetrap one would go the other way, just so that you can take a smaller voltage and crank it up.
Okay.
So what a transformer does is it changes voltage from one type from one amplitude to another. And this is the reason why AC power was used in the United States, is the fact that because we have such open space here, if you're doing DC, there's much more significant loss when transmitting long distances with DC than with AC. With AC, because we have the transformer invented by
Tesla?
That's right. And who made a fortune off of it?
Not Tesla?
Westinghouse, more specifically.
Not Tesla.
I don't remember.
Yeah, no, not Tesla is usually a good, who made a profit, not Tesla. So this allowed us to crank up voltage to incredibly high voltages for traveling across great expanses of land. Now at this point, Europe does something similar. They do have transformers, even though they're doing DC, but they have oscillating DC.
What? That's
Wait,
just
how does
AC.
that work? Is that how it is?
AC, the current flows this way, then that way, then this way, then that way.
Oh,
Oscillating DC goes this way, this way, this way, that way.
oh.
It's just not one, like, it takes breaks, it pauses.
Well, it does in both cases. Because, it stops in order to turn around.
I see.
Well, I'm saying like normal DC doesn't, it's just
Right.
straight, that's the difference.
Yes, compared to normal, I'm using a battery, yes. All right, so over here on the primary side, I have N sub P coils. I have epsilon sub, I'll just call it P for primary. So I have this current that's oscillating back and forth here. Because it's oscillating back and forth, well, because I have a current, I have a magnetic field here. This bit right here is some sort of, you should think of them as iron cores, but I don't know what material they're using today. This basically creates, it's kind of like a waveguide. It creates a magnetic field in this core here, this what I've now striped in green, which then basically transfers over to here. From what I was reading, they're usually about 99% efficient. So as this oscillates back and forth, as we have a current, we get a magnetic field. As the current changes, we get a change in the magnetic field, which means we have a change in the magnetic flux, which means that we're going to produce an EMF, a voltage. Over here, we have N sub S coils. We'll have a voltage that is created between these 2 points right here of what I'll call epsilon sub S. Let's just go ahead and establish that epsilon sub P is equal to epsilon sub naught cosine of omega t. So it's oscillating back and forth. I could have picked sine. I just stuck with cosine. That's what I did. All right, so on the primary side, the magnetic field that is created is mu sub naught in sub I. Lowercase I because we're dealing with alternating current. This lowercase n, oh, I should put a P there, and that's a P. The lowercase n is the coil density, as you have all measured at some point or calculated. So it's mu sub naught times the number of coils on the primary side times I sub p over the length of the primary coils. That L sub p is the physical length. That's L sub p, and that length right there would be L sub s. Excuse me. We're dealing with an inductor here. We got a loop of wires. Presumably that they are thick enough so that the resistance is low. So not dealing with any significant resistance there. But it's just it's a coil of wires, so I'm dealing with an inductor. I know that for an inductor, if you think back to the phasor diagrams, if I have a voltage here, where is the current?
It's 90 degrees ahead.
So current comes before the EMF?
No. It's 90 degrees before it. So like voltage is ahead of the
All right, so you two are completely opposite there. What you're thinking?
well, the voltage should be ahead of the inductor by about 90 degrees.
So it's just, you remember that?
That's Eli the S one.
Okay, so you're using that?
Yeah.
Okay. Eli, L, inductance, voltage comes first. So, if no, I'm gonna do it that way. All right. What do you know about the voltage across an inductor?
Well,
Sorry. So for a resistor, it's current times resistance. For a capacitor, it's charge divided by the capacitance. What is it for an inductor?
charge divided by the charge divided by the capacitance still no. It's just instead of
Is it,
I'll say no.
is it charge divided by inductance? Or is it charge
No.
multiplied times inductance?
All right. So apparently, either I skipped over it too fast, or your memories are that of an old man. I know that the voltage across an inductor, negative L delta I over delta T. I'm not worried about the plus and minuses, so my minus signs will just sort of disappear as we go. So if I'm looking at my voltage here, I've got a voltage of epsilons of P going from here to here, because again, voltage is between 2 points. That also would be the voltage across my inductor. So in essence, I've got my epsilons of P is equal to, and again, ignoring negative signs, delta I over delta T. This is epsilons of naught cosine omega T is equal to L delta I over delta T. Well, let's get it. We're trying to solve for the current, so I can plug into here. So my current, so my change in current over time is equal to epsilons of naught over L cosine omega T. So what is going to give me a slope of cosine? This is just slope of current versus time.
Sine.
Yeah. So my current is going to be epsilon sub naught over L omega sine omega T. And we did this when we derived the inductive reactance. We did this. So my current in the primary here, therefore, or sorry, my magnetic field is mu sub naught. Actually, I should not have a sub-zero there because it's not free space. We do have an object here. So it should just be mu. All right, so mu n sub p over L sub p. And then times my current, which is epsilon sub naught sine omega t over L omega. That's a capital L. And this is primary, so that would be L sub p. Omega will be the same for both. And I got my subscripts on. Subscripts are good. All right. And the rest is obvious. Where am I going with this?
We're trying to find the magnetic field, right?
Yeah, well, we found the magnetic field. That's the formula for the magnetic field on the primary side. That'll be the magnetic field on the other side as well. Because of this core right here, and it does manage to transfer pretty much all the magnetic field. It's created here, it transfers through, and we get this continuous loop here. I'm trying to figure out the EMF that's created on the secondary side. I know that that on the secondary side is going to be equal to the change in the magnetic flux on the secondary side over the change in time. Again, I dropped the negative sign because that's irrelevant to what I'm trying to do right now. Magnetic flux.
B cross A.
B
A cosine theta.
Yeah, which is the dot product.
Oh, it's dot.
So I have the change in dA over the change in time, and this is all on the secondary side. Now, given that we just did the product rule applies here, except for the fact that A is constant. I have these coils with some area, cross-section with the area of the coil itself. That's not changing if it's a properly made transformer. So area is constant, but if I did the product rule, that would be the change in, so that's A change in B over the change in time plus B change in A over the change in time. Area's not changing. That goes away. And what we're left with here is just the area of my secondary coils times the change in the secondary magnetic field times time, or divided by time. Now we are going to make the assumption, and we could, in theory, make a transformer differently, but we are going to make the assumption that the coils on the primary side and the secondary side are the same size. What's different is the number of coils, but the actual coil, a single coil itself would be the same size. In other words, A sub S is the same as the area on the primary side. Bs is equal to Bp. And so that's area on the primary side times the change in Bp over the change in time. Well, I know what Bp is over there, so that's the change over the change in time of mu in, so P epsilon sine omega, epsilon sub naught sine omega t over L sub little L sub p, big L sub p omega. I didn't see that I could have got a step out, but oh well, we're here now. I'm doing the change in time, so of all the stuff here, mu, n sub p, L sub p, big L sub p, omega, none of those change with time. So I'm just gonna factor those out. So I'm left with AP, U naught, NP,
Did we just say U?
Mu.
U, yes, you were right. NP, epsilon sub naught over LP, omega, and then the change in sine omega t over delta t. No, I took that into account there, okay. Oh. I do need to make one adjustment here. So questions up to here before I make my adjustment. One thing that I did leave off is this idea of the areas that, the area is the total area. So one coil has an area of A sub S or A sub P, but I've got more than one of those, so I need to multiply. So this A sub S really is the number of coils times the area of a coil. So N sub S, A sub S is the total area on the left-hand side. N sub P, A sub P would be, oh sorry, on the right-hand side, and then this one on the left-hand side, the total area. Those are the same. So A sub S is equal to, let's see, so A sub S, A sub B, so this would be N sub S, and the total area, yeah, A sub B. So if I let A sub S equal A sub P just equal A, then that becomes N sub S, and the area of P it's a key thing that I just skipped over there. Let's see. Yes, that stays the same. That's the D N sub S there. Oh, okay. So that's A times, start taking that into account. Seems like I hit it. I did not, okay. My memory was different than what I'm seeing right there. Okay, good. I didn't need to erase all of that. Oh well. So number the coils on the secondary side, A times delta B over delta T, which is over there, mu, N sub P, epsilon sub naught, sine omega, epsilon sub naught over L sub P, big L sub P, omega, and then we get the change in the sign of omega T over time. And the change in sign,
Cosine.
and so we end up with, and then the omega pops out using the chain rule. So I have n sub s, a, mu, n sub p, epsilon sub naught, over L sub p, big L sub p, omega, times omega cosine omega t.
If we lose mu,
The mu right there. What's the formula for inductance?
The 1 over square root of 1 minus something squared.
No, it sounds like you're thinking of the Lorentz factor.
what you said, inductance?
Inductance.
Not really,
Well, I guess I'm-
1 over, no, is it 1? No, it's just omega L? No.
That's reactance.
That's
That's inductive reactance. All right. You did this on the lab. I assume you would just look on the first page. It's gonna be mu n prime for the primary side squared a for the primary side, which is the same as the other side, over L sub d. So plugging that in for L over there.
World's longest equation.
So this is epsilon secondary is equal to n sub s times a times mu times n sub p epsilon sub naught over cosine omega t over little l sub p, the omegas that cancel out, and then on the bottom here, I've got a mu n primary squared